collaboration. That's why institute name was Mahindra Ecole Central. Now we are full-fledged university and we have the full name as Mahindra University. But the engineering division of our university is still Ecole Central School of Engineering. So that's about my institute name. And so just now, as you see that it's 20th May 2020, we became the university. And we have basically 4 branches for the students. And so we teach mechanical engineering, electrical and electronics engineering. We teach civil engineering, computer science engineering, artificial intelligence engineering, and yeah, and one more branch I think is also there, which is started this year. Yeah. Maybe it's not given here. Yes, it's here. So we have civil, computer science, electrical, electronics, mechanical, humanities, mathematics, physics, and chemistry. So all these departments we have, and specialized engineering branches, we can say that it's only 4: mechanical, civil, electrical, and computer science. And apart from them, we have started new branches: artificial intelligence, and one branch on advanced physics. So that's all from my side. And just one more thing, I am teaching manufacturing subjects over here, and also robotics as my main subject, because we did PhD in robotics. So that's also I'm teaching. So now I would like to switch to my slides. Okay. So kinematics of machine or mechanisms. So we are going to talk about that. So imagine being on a design and development team, the team which is responsible for the design of an automotive windshield or wiper shield for your car. So when you're proposing a vehicle, it could be a sports model, or it could be a normal model, or it could be an model which you can use for racing cars. So any model, but it may need wipers for the rains to protect, means to make you able to see or visualize through the glass in the rains. So on the first design task in determining means first you have to determine how you will put the wipers on the car, what will be the range of those wipers, how they will move, and your movement should be sufficient to ensure the critical positions of the windshields to be cleared. So means wherever your wipers are moving, it should clear that area where, so that you will be able to see it, right? um, Once the desired movement has been established, and an assembly of the component must be configured uh, to move the wipers along the pattern. So whatever pattern you have decided, like it should uh, move every 1 second or 2 seconds or 3 seconds, which mode you're selecting depends on that. Uh, the subsequent tasks, including analyzing other motion issues such as timing of the wipers and whipping tendencies, how it is doing. So for the wiper system, like most machines, understanding and analyzing the motion is necessary for proper operation. And these type of movement and motion analysis are the focus of this subject or this topic. So another major task in designing machinery is determining the effect of forces acting in the machines. And these operates, your machine, when your machine is running, obviously some forces will be acting on it. So the forces also dictates the required strength of the component. So at some component you will see less forces, and some components you will see more forces. So depend on that, you will also have to design your component, how strong those components should be to handle those forces and transfer the motion, right? So For instance, the wiper system which we were talking about here, uh, the wiper system must withstand the friction created when the windshield is coated with chaff after the car has been parked under a tree. So this type of force analysis is a major topic in the later portion of this uh, topic. Like, so yeah, I have already covered all this. So let's go and talk about mechanisms and machines. So machines are actually devices which used to enter, transmit, and direct forces to accomplish a specific objective. Okay. Example is you can see a chainsaw is a family of machines that direct forces to the chain with the objective of cutting wood. And mechanism is the mechanical property of machines that has the functions of transferring motion and forces from a power source to an output, right? So here I am showing you one example, and so in this example you can see that it is a adjustable height platform. So you just have to pull the lever so that your platform can move up or down, and you have various number of linkages over there, uh, which with the each push of your lever, um, these links will move a little bit so that your lever will move up to a certain height according to how much you have pushed your lever, right? So you are seeing that you have a platform on which you will stand or which is moving up and down. Below the platform you have some number of number of links, and on based and below that you have a base and a lever which you will pull or push to move your cylinder. So it could be either connected with hydraulics, or it could be connected with screw and nut arrangements to move this platform up and down. Okay, so most of the times it is connected with hydraulic cylinder which will move this platform up and down. So although the entire device could be called a machine, so when you will I'm asking you about all the device, you will call it as a machine. But when I'm talking you about the part of mechanism, so mechanism you can say uh, so it's considered to be a rigid part. So basically mechanism is can be considered rigid parts that are arranged and connected so that they produce a desired motion of the machine. So what is the desired motion? The desired motion is you should be able to move this platform up or down. Okay, so the purpose here is means in terms of mechanism is you should be able to move this platform up and down, and the mechanism which is involved here is it includes links and hydraulic cylinder and this lever over there, right? So these are actually transferring the forces to move this platform up. Okay, so this is just one example to tell you what's the difference between mechanisms and machines. So what initial setup you have to do for doing this? So the question comes, what is the significance of the leg length that supported the platform? So you are seeing these leg lengths which are supporting the platform. So what is the significance of that length? Uh, Second question, it could be, is it necessary to support legs to cross and to be connected at the midspan? Or can we connect the legs in some other way? Maybe not in cross, maybe straight, vertical, or maybe some other profile if you can connect the leg to achieve this mechanisms of motion. Or how far the cylinder extend to raise the platform. Okay, so or is it better to arrange the so that it's cross closer to the platform? So the position of the cylinder or screw nut arrangement or whatever you are using, how where you will place them, and so that you will can get better forces distribution so that you can move your platform up or move the links accordingly, right? So so that's the initial step that you will see when you will designing this or when you're seeing this example. Okay, and Second step can be means the can be about the dynamic forces analysis of the platform. Could we provide insight into another set of it's called another questions when you are designing it. So what capacity is required of the hydraulic cylinder? So weight depends on how much load your platform can take, okay, or how much load your platform should be able to take. You will decide uh, what will be the size of your links, how heavy it should be, what will be the capacity of your hydraulic cylinder. Is the platform free of any tendency tip over? Means it should not be like that it's tip over or it's topple when you are at some other corner. So accordingly, you have to overcome those problems, right? And then you can also check whether what cross-sectional size and material are required of the supported legs so that they don't fail. It should not be like if you are having some load over here, or if some person is standing on the platform, these legs get bended, okay, or they got broken, or they got distorted in shape. It should not happen. So you have to select the material accordingly for designing it, right? So this is the part of dynamics that you are seeing. So you are basically seeing all the forces over here so that you can achieve a particular motion. And in kinematics, you are seeing all these things that all these questions that we were talking about, right? So kinematic analysis and synthesis, when we talk about, so kinematics actually deals with the way things move, okay. And kinematic analysis, so what analysis you do, so it basically determine what is the position. Means so in the last example that we have seen, so position means, let's say it is at 0 0 when it is not open, and when you pull the lever and it goes up, so at what position actually it is now, how much displacement does it have, is it having any rotations, what is the velocity with which it is moving, and what is the acceleration, okay. So all these things are the kinematic analysis part, means these parameters. And for measuring these uh, parameters, you have to provide either geometry, dimensions, motion path, and etc. for determining these position, displacement, rotation, velocity, and acceleration, or to analyze the kinematics, right? Now, synthesis means you are determining geometry, dimension, and operation range. So, means it's for designing, means you're synthesizing. So first you did the analysis, and then you're synthesizing. Okay, after analysis, you may determine uh, in synthesis that this should be the geometry, it should be the dimension, and some operation range should be there. And for that, you have to decide what position, what motion path you need, where what should be the position where it should reach, and what should be the velocity. So like that, you can synthesize your uh, kinematic, kinematic synthesis you can do. Okay, so now there are some terminologies that will come into picture in while we are discussing this topic. So first is degree of freedom. I think I expect that all of you already know what is degree of freedom is. So you are seeing that I'm showing three axes over here. That is X, Y, Z. So if you are in any direction, if you have free motion or you can move in any direction, so the motion in that direction you will consider as degree of freedom. Okay. So here you are seeing that you have rotation about an x-axis, any axis. Okay. Then you have translation in any direction. So in our 3D space, we have 3 rotation and 3 translation, right? So total 6 degree of freedom you are seeing over here. So if you're considering a point in air or anything in air, that will have or you can just consider a ball in the air. So that will have 6 degrees of freedom in space. Okay. Another example we can take. So let me just move to pen. Yeah. So let's say we have a table. Okay. And on that table, you have a book. One book is there. This is your book. Okay. So if I ask you what is the degree of freedom for this book, okay, and you have to answer your question so that any face or your book should not leave the table. Okay. So I will ask you what is the degree of freedom for this book. So you will see. Let's try it. This is your, let's say, x-axis. This is your y-axis, and this is your z-axis. So along x-axis, you can have translation, means your book can move in the table like this. Along y-axis also it can move like this. And along z-axis it cannot move, otherwise it will leave the table. And that's the obstruction is over here, that it should not leave the table. So you can have translation motion over here. Okay. You can give a rotation along x, but if you are giving it, this face will leave. And so this face also should not leave the stable surface. So in that case, rotation will not be there along x and y, but along z you can have a rotation. So total 3 degree of freedom you can have it here. So it is just one simple example that I would like to give you. So I hope you already understand what degree of freedom is, because it will be very useful when you are going in future and seeing any things in that perspective. Okay. So when we are going in real world, actually you will not have joints like this book. You will basically have joints um, either in terms of hinges or some prismatic. So book motion you are seeing here, it was prismatic plus revolute joint. So you can have two kind of joints, either revolute or prismatic. Okay. So and other joints are part of these joints, means mix of these joints only, means revolute and prismatic only. So here you are seeing an example of lower order joints where contact is surface. Okay. So this is your spherical joint. This is your universal joint. Okay. So in spherical joint, you have motion along all the 3 axes, means rotation along all the 3 axes, but no translation. In this universal joint, you have rotation along one axis only. So this is that axis. Here, in case of book, as I told you, this is 2 translation and 1 rotation. Here you have prismatic joints. Only this bar can move, go in and out of this. So here you have prismatic motion, 1 degree of freedom. And this is your cylinder. So because you do not have any restrictions over here, so it can slide on this bar as well as it can rotate. So 2 degree of freedom you can have over here. Similarly, if you put some threads on it, there also you will have some translation as well as rotation motion. Okay. So you have a spherical joint, revolute joint. This you can call as planar joint, prismatic joint, cylindrical joint, and helical joint. But main joints are revolute and prismatic, and all these joints are mix of only revolute and prismatic. Okay. Then comes the higher order joints where you have positive contact. So positive contacts you will get only in gears. Okay. And here the motion is through a point. Okay. So in gears as well, either it's a point or a line, so on which that point is. Other example is cam joint. So here, this is also the place where you can have a motion along a point. So here you can see, because both are cylindrical surfaces, you will have motion along a point, but that point will be coinciding with a line only. And So when you're seeing from the front, if you're standing over here, so you will see it as a point only. Okay. So a cam joint which you're seeing here is means it allows both rotation and sliding between two links. So when your cam is moving, it will provide rotation as well as sliding. Okay. So when the longer side will come, it will slide, and this thing is rotating. Okay. So here you have rotation motion as well. So it comes under higher order joint and also called as half joint, this cam joint. And gear connection means that you're seeing is allows rotation and sliding between two gears as their teeth mesh. And sliding between the gears means the arrangement that you're seeing here is also in higher order joint. We also call it as gear drives at positive drives because you will not have losses over there. Okay. Now, there are some more terms that will come that's called as link, or here I am talking about simple links. So simple links are nothing but it's you can say it's a rigid body that contains only two joints which connects it to other link. Okay, so maybe one link is before it and other link is before after this joint. So it's basically connecting um, with other links. So it's like you are just connecting two points and it's making a link. So whatever is the shape, this joint position you will consider as 2 points and you will connect it. Okay. So it could be like that, this as well. So what this means, let me just draw it. So let's say your link is something like this. Okay. So in this case also, if I ask you to draw this link in terms of uh, line, so how you will draw it? You will draw first 2 points, you will join them. Okay. And then whatever shape is there, maybe it could be a triangle or something, that shape you will just give it. Okay. So basically your link is defined by these 2 points connecting with a line, even though in actual figure you will not see this line. Okay. So, so basically you can consider a rigid body that contains two joints. Then uh, you can further simplify means a crank you will see in an example of a link. So it's a simple link that is able to complete a full rotation about a fixed center. Okay, so that's one example of link. Rocker means a simple it's a simple link that oscillates through an angle. So it will, so any link that you will see here in coming topics which is making complete rotation, that link you will call it as crank. And rocker, it's actually a link, but it will not be able to complete full rotation. So it will always oscillate through an angle. Okay. So that you will see in future slides what a rocker means. But simply, crank can complete full rotation, but rocker cannot. It's very simple here. Rocker will do some oscillation. Sorry. Now, the thing that I was telling you, so a link with point of interest. So point of interest is here is this the example that you're seeing over here, that piston cylinder bar. So sorry. So here you can see that these are the 2 points of interest. So we just connected it with like this along the line, and the remaining shape we made it with a line diagram like this in triangle form. So this triangular is your link. Okay. Similarly, you will have some complex links, and so complex links is also a rigid body that contains more than two joints. So previously you have in simple link you have only two joints, and complex link you will have more than two joints. And so if I see a rocker arm is a complex that you're seeing here, it's a complex link where you have three joints. This is also a three joint part. Okay, so these are the part of complex links. So for example, this one you can draw it like this, but you have to show the joints as three over here. Okay, so you will have more than two joints. Previously you were showing two joints only. There you didn't show any dot or point for motion, but here you will have three joints, means three links also can be attached over here, these joints. Okay, now some other terminology. So in mechanisms you can have planar or spatial mechanisms. Okay, so planar mechanisms means the mechanism that works on a plane, generally on xy plane. Okay, and spatial mechanism, it's simply the extension of planar, is like mechanisms that works in the space, but now it is in 3D plane or xyz space. Okay, so planar can just one example of a simple example of planar mechanisms that we talked about book. So that's planar. Spatial mechanisms, so it will work in 3D space. So anything which is moving in 3D space, that will be spatial mechanisms. Okay, so you will have x, y, and z motion. So anywhere in this x, y, z, you will have motion. So this is the example of planar mechanisms that you can see. So the motion on the end effector, or you can say the uh, performer is in the middle, and it is moving always in a plane. Wherever your directions goes, it will always move in a plane. Similarly, in these examples, you can see that uh, this is your end effector, and when you have any motion over here, it will always move in a plane. So yeah, this is planar mechanism. Spatial mechanism, you can see here you have linear actuators. These are the 6 linear actuators that you are seeing at the 3 corners that you are seeing. So it is uh, you can call it as delta platform, or you can call it as I've got the name. Yeah, 6. So this is a kind of a robot which is like 60 of freedom robots, because you have 6 joints. 1, 2, 3, 4, 5, 6 joints you have over here. So 3 joints over here and 3 joints over there. And so when you move these linear actuators up and down, this platform will actually go it will not be in one plane, it will go in some other plane as well. Similarly here, this delta robot that you are seeing, it will move, it is used for pick and place over here. So this conveyor belt, some objects are going, it will pick and place it. So this will also move in 3D space. Okay, so that's example of spatial mechanisms. Your simple robot arm, if you have seen it in industry, maybe in automobile industry, which looks something like this. Maybe at the end you will have a gripper which is taking something. So that's a spatial mechanism. From nature, if you want to take any example of spatial mechanisms, your arm is a perfect example of it. Okay, because arm can move in anywhere in 3D space. Okay, now let's take one example. And here you can see that this is a shear press. It is used to cut and trim the electronic circuit board or any uh, sheet if you want to cut it. Okay, so the question is, draw the kinematic diagram for this link. So what do I want? So I want you to identify the frame, okay, in which frame it is moving. Identify all the links that you and there's this mechanisms or that this machine is having. Identify the joints. Identify any points of what you say interest means fine that you have, and draw the kinematic diagram. So using the link line diagram, you have to draw a kinematic diagram so that you will have connections over there. Okay, so you can take a minute, try it by yourself, and if you have any problem, then uh, just take a minute, just think of it, and uh, try to draw the kinematic diagram of this figure. Please try it. After a minute, I will show you how you can do it, and then I will give you an assignment so that you can do it in home as well. Okay. So I hope you have just visualized maybe in terms of how you can draw the line diagram, but I would like to show you here how you can do it. So how many joints you have it here? So this is your joint number 1, joint number 2, joint number 3, and joint 4 here from you have to consider because your link is extended over here, but it's not a joint, but because link is there, so you will go till there. And this link connection you have to give through a line like this till there. So it will make a triangle where you will have another joint over here. Okay. So determine which part is fixed or which one is moving. So that's the first objective. Your means your first. This should be your first objective. It means you have to determine what is the frame in which you are having the motion. So once you determine the frame in which you are having the relative motion, then it will be easy. So here you are having the relative motion over here along the base, so that can cut something. Okay. So this is your moving part. This is your fixed part. Second, determine the numbers and types of joints. So here you have revolute joint, revolute joint, revolute joint, and this is your sliding. Third, determine the links. So you have link 1 and this is your link 2. Okay. Determine the draw the kinematic diagram of this thing. Okay. So here you can see that lever, we can draw it as a triangle. It has connected with this hinge and one joint over here, A and B. Here is your cutter, which is connected through this lever by a link. You can see here by a link. Okay. So this is your third link, your cutter, and fourth link is your lever. And first is your fixed, this hinge where it is attached link. So totally 4 links you have. This point, this joint you can consider C, and this motion prismatic you can consider D. So link 1 is fixed part, link 2 is your handle, link 3 is your cutting blade, link 4 is the bar that connects the cutter and the handle. Okay. So actually you have relative motion over here, but also you have one constraint over here so that your cutter should not go in any other direction, maybe here in horizontal direction. Otherwise, when you are moving the lever, it may be hanging and oscillating. So you should have to restrict the motion in which it should cut. Okay. Then point of interest we have to see is here. So we have joint A, B, C are the revolute joints, and D is your prismatic joints along which you are doing the cutting. Okay. So similarly, you have this example. So this is your water nozzle or automatic car wash. So a linkage is used to operate this water nozzle at an automatic car wash, right? So you have to draw the kinematic diagram for this example that you're seeing over here. So this is your assignment number 2. and find how many joints and links are there and how you will draw the kinematic diagram for it. Okay, so this is your exam assignment, and that you can do and submit it and show it in the next lecture. So Latifa, when they should submit it? Do you give any 1 day time or 1 week? How you do it?
So as you wish. So student can submit until when?
Because it's a very simple example, I think they can do it in a day, maybe today and tomorrow. By tomorrow they can submit it.
Well, students can submit it up to this evening, and Thursday you can discuss it.
Okay, so I will share a folder, and the students just have to do it in on pen and paper, or if they want, they can do it in Word as well. And they just have to submit that file either in the form of image or in PDF. So the folder that I will share, you have to just put everything in that folder. So it will be kind of a link in which you have to submit, but you cannot delete anything from there. Is it fine, Latifah?
Okay, so I think student can submit it in our platform. You
Okay.
can see it as well.
Okay.
But the deadline, it's up to you. Either this evening or tomorrow or
Uh,
when. And I will make the platform for you so the students can submit it.
okay, I think this evening is good.
All right, so let's say at 6 maximum.
Okay. And I will just discuss you I can make that folder, means how I can see the assignments they have submitted later after the class. Okay.
Okay.
Okay. Okay. So now let's move to Grobler's equation. So uh, uh, when you're seeing any mechanism, so it will be forming number of links. It will have number of joints over there, and by seeing the mechanisms or the machine, if I ask you how many degree of freedoms uh, are there, means how many joints are there, how many degree of freedom that uh, mechanisms or machines have, how you will find it, because sometimes it becomes very complicated to determine whether it is 1 degree of freedom or 2 degree of freedom for any number of joint or link. So what you will do, you will use this equations that you're seeing here. So it's nothing but it has f is degree of freedoms of mechanisms, n is your number of links including the fixed link, j is number of joints, fi is degree of relative motion permitted by joint, okay, and lambda is degree of freedom of the space in which a mechanism is working. So lambda is equal to 3 for planar and lambda is equal to 6 for spatial, means for 3D. Okay. So normally it becomes like for planar it becomes like plus this fi. So fi degree of relative motion permitted by the joints. So for simple cases, we just have this. So like this you will write for planar, and whatever fi is there that you will write. Similarly for lambda you have to just put 6 over here, and whatever fi is there that you have to put. Okay, so the degree of freedom of the following mechanisms can be deduced by Glauber's equation. So here you are seeing that if you are moving this link or this joint through this joint, if you are moving this link number 1, so what you will see, it will rotate, and because of its rotation this link will move and this link will also move. Okay, and the link which is means joint which is fixed, you will consider both as one, this and this as one joint only. Okay, so single degree of freedom you are having here, that is m is equal to 1. Okay, this is your locked mechanism, because with this mechanism you will always get, when you are rotating only one link, you will always get one kind of motion. So that single degree of freedom you are having over here. Here you are having locked mechanism, because either you move this or this, your mechanism will not move. Okay. And then here you will have multiple degree of freedom, m is equal to 2, because here you have a slider as well. It's not fixed. Okay, so this is your slider. So rotation as well as sliding, so two kind of motion you are getting. So that's why m is equal to 2. Okay. So now let's do it. Means let's try it and put it in Grubler's equation. So basic Grubler equation, because this mechanism is working in a plane, and you already know what is the relative degree of motion permitted by the joint. Okay, so that you also know. It's all also in one direction. So Grubler's equation, you can write it in something like this: 3n minus 1 minus 2j minus is 2jp minus, so one more joint you have, that is joint uh, is higher order joints. If you have cam or gear joint, so that you don't have. So total number of links in the mechanisms are 1, 2, 3. Okay, so you have 6, and total number of joints for rotation, if I see, so you have total number of links are 4, and so this link you will also consider. So here you will have 9, and total number of joints 1, 2, 3. So it's not communicated. Yeah. So I will go with this 1.1a. So here you are seeing the single degree of freedom. So that's you have most linkages used in machines have this degree of freedom A. Okay. So that's why it is 1 degree of freedom. So it's directly after seeing also you can draw it. So 1 degree of freedom that you will get. So use this equation so that you will not have confusion. So here you have 4 number of links, joints, and 1, and whatever direction of motion that you are having. So that will give you 1. So don't use this formula. So it's for simple higher order equations. So don't use this one. Okay, now here you have assignment number 3. So this is your special mechanism. So here you have 6 UPS simulator, and you have to draw the kinematic diagram for this. So you have to compute the degree of freedom for this. So you have to see number of joints and number of links over here, and then you have to see what you will get. So this is good example to explain this. So n is 14 that you see, 1, 2, 3, 4, 5, 6. Okay, so 6 links you are having directly over here, and then you have uh, one platform over here, one platform on the top. Okay, and these links are also moving up and down. So means these one will become 2 because it's not fixed between two joints. So it is moving. It's prismatic joints you are having. So at this place we are having 2. Okay, so that's 12 plus 2, so total 14. Joints you are seeing here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 joints, and 6 prismatic joints. 12 plus 6, 18 joints you have. And then comes this Fi. So Fi you can see it is 6, and lambda is also 6. So because it is in 3D. Okay, so 6 motions you can have. So when you will just put it over here, you will get your degree of freedom equations, right? So this is your group task that you can take a week, or by next Thursday we will discuss it. So when we'll have next lecture. So these are some link mechanisms like 6-bar linkages, Scotch and yoke mechanisms, slider crank mechanisms, Wengel needle mechanism, Stewart Go platform. So this platform that you are seeing, so we also call it as Stewart platform sometimes. Okay, Stewart Go platform is a little bit different, so that you can see it will have universal joint. Then you have Agile Eye, cam and follow mechanisms, 3RR mechanisms, Tripteron and Delta robot. So Latifa, how can we divide this group task?
So overall, there are 50 students.
Mm-hmm.
Okay, sorry. So there are 52 students. You have 10 topics. So I would say one group will be 5 students, and maximum 6. There will be 2 groups with 6 students. Usually I will call who will be the leader. So I will call 10 students will be the leader for each group.
Okay.
And other students can join wherever, which group they want to join. But for this, up to you. How do you think?
I think if you have 60 students, 6 per mechanisms we can assign.
But there are only, so today there are only 50 participants. So one group will be 5 students, right? Maximum 6.
Okay.
So I will put it in average. So remember, students, minimum number of students in one group is 5 and maximum is 6, not less than that.
Okay.
So how do you think you want to distribute this? I will call
5.
I will call the students who will be the leader. What do you think?
Okay.
So group number 1, I will just call from here. And I will, wait. I will note down from number 1. So group number 1. Okay, wait, let me check here. So group number 1 is Bimo. Bimo, are you here? Bimo Satrio.
Yes, ma'am.
So you will be the leader for group number 1.
Okay.
Group number 2, Farah Judith. Farah, are you here?
I'm here.
Okay, group number 2, group number 3. Number 3 is Muhammad Akila.
Yes, I'm here.
Okay, you will be the leader for group number 3. Group number 4 is Marsha Haya Akila. Marsha?
Yes, ma'am.
Okay, you will be the leader for group number 4. Group number 5. Number 5 is Sunu Dwi Nugroho.
Yes, ma'am.
Okay, you will be leader number 5. Number 6 is Rahmat Agung Wicaksono.
Okay, ma'am.
Rahmat Agung, number 6. Number 7. Number 7 is Nandana Gozi Alif.
Yes, ma'am.
You will be number 7.
Okay, ma'am.
Number 8. Number 8 is Fifi Bella.
Yes, ma'am.
You will be the leader number 8. Number 9. Number 9 is wait, let me see. Anggito Kusumo.
Yes, ma'am.
Number 9. And number 10. Number 10 is Ambrosia.
Yes, ma'am.
Okay, Deep, I have distributed to
Okay,
all
so
10 students who will be the leader, and the rest of the students, please join to which group that you are interested in.
okay. So Latifa, I would just like to take 2 more minutes.
Yes.
For degree of freedom minus 2jp minus 1jh. So here jp is your joints, which includes pin and prismatic joints, and jh is your higher order degree if you have any gear or something. So in these mechanisms that you see, n represents number of links. So here you have 4 links. So this hinge, you will consider only one link. 1, 2, 3, 4. So 3 into 4 minus 1 minus 2 into number of joints that you have. So 1, 2, 3, 4 into 4 minus 0. So it will be 1. So that's how you are getting m is equal to 1. Now for this, if you see, you will get 3 into 3 minus 1 minus 2 into 3. So you are getting 6 minus 6, that is 0. And here, because you are having one more of the means one more joint will be there, that's prismatic. So that will be 3 into, so 1, 2, 3, 4, 5 minus 1 minus 2 into, so how many pins? 1, 2, 3, 4 and 5. Okay, so into 5 prismatic joints. So means 1 4 revolute and plus 1 prismatic. So that's how 5. And here you will get 12 minus 10, that's 2. So that's how you are getting 2. Okay. Yeah, so that's all. I was because it's very old for me, so I got confused over there. So now it's okay. So that's all. I think, I hope you understand what we discussed today. If you have any questions, you can ask, or we'll meet on Thursday with your group tasks.
Okay, Deep. So this group task will be Thursday next week or this Thursday?
What you suggest?
I would suggest either Monday or Thursday next week.
Okay, so Monday is good.
All right, so Monday next week, so they will have some time to prepare.
Yes.
I
Even though,
will.
because I think it's only 5 students each group, and it's only one links that they have to perform, so it should not take much time.
Yes.
Still much good.
Yeah. So Monday next week, please pay attention to all 10 groups. One group will be given about 5 minutes, the 4 minutes maximum presentation. Right, Tip?
Yes.
And what you will have to present is basically you have to present about the mechanism how it's moving, what is the degree of freedom, then you have to apply the formula that Mr. Tip has presented and define how many links, how many joins, how many degree of freedom, what is the function. And if you can show the video from anywhere from internet, that would be plus. So everything is written down here. Show the video, draw the kinematic diagram, find its degree of freedom, and also mention its applications. All right, we will share this in PDF in Classroom. Our platform names is Classroom, Dib. So
Yes,
we will
yes.
share this material in Classroom so that you
Okay.
can download it. And also for small assignment, I will open for you to submit up to this evening, let's say up to 6 p.m. Okay, students, so 6 p.m. for today's short assignment. Okay, so do you understand? You have two assignments. The first assignment is just to define the kinematic diagram. That's until 6 p.m. today. And you have this group assignment for Monday next week. Is there any questions? Do you think Mr. Deep speaks too fast or it is okay? Any comments?
Yeah, if you think my pace is too fast, you can just tell me. I will make it slow, or if you think it's too slow, I can make it fast.
Mm-hmm. Is there any questions? No? So if there's no questions, I have shared the code for today's attendance.
Farah has some questions. He raised a
Yes.
hand.
Mm-hmm.
Farah?
Sir? Yes, I'm
Yeah.
sorry. Could you hear my voice?
Yes, yes.
So, Mr. Drip, could you please explain more about how to make the kinematic diagram? Because I guess you explained it too fast, like how to determine the fixed and moving parts and the numbers, the links, etc.
Okay.
Thank you.
So we have seen two examples over here. So one is this one.
Yes.
Other one is the assignment that you have to do. Okay. So what basically you have to do. So this is your mechanisms, or this is your machines from which you have to draw the kinematic diagram, how links and joints are connected together and how you are having a motion. So first you have to see in which frame you are actually achieving the motion. So you will see here you have your cutter. Okay, so this cutter will move actually up and down to give you cutting motion. So this is your cutter. This cutter is attached with a joint and through a link to this lever, which you have it over here, which also have a joint. So these two joints is connected with a link. And when you press this lever, this cutter will move down, or if you pull it up, cutter will move up, right? So now if you want to draw this kinematic diagram for this thing, so it's like just a line diagram. So let's say this joint, let me just draw it here. So this is your joint, this is another joint, this is another joint. So here you having your moving motion, and this part is fixed. So fixed means, as I told you, fixed, whatever is fixed, that you have to consider only one link. Okay, so this portion and this portion, that you will consider only one link. So through this link, this motion you are having, and that's prismatic joint. So you are having another link over here which is moving. Okay, so you have this joint, this joint, this joint, and this prismatic joint, which is giving you motion for up and down. So four joints you are having, three revolute and one prismatic. I think till here it's clear. Now let's see the links, how many links you have. So link number one is this fixed one. Okay, So that is your link 1. Link number 2 is this lever. Link number 3 is this, and link number 4 itself is a cutter which is going up and down. Okay, so the same thing I have explained over here. So this is your diagram. This is your fixed part, this A. So here you have a joint A, and 1 is your fixed part. Then you have another link 2, and B is your joint. So B is this joint. Okay, so this is joint A, this is joint B, this is joint C, and prismatic joint is joint D. Okay, so joint D is prismatic joint. So this link, because you are giving your force over here. Okay, so here you have your handle from where you will push or pull. Anything you can do it to move this thing up and down. Okay, and this lever, if you see, it's constrained in a space. If it is not constrained, what will happen when you pull the lever? This thing can oscillate and can go anywhere. It obviously it will go up and down, but it can go in any direction, up and down. Okay, so that's why it's constrained, and you are having prismatic joint over here. So this is your link number 2. This is your link number 3, and this is link number 4. Anything you can consider 3 or 4. It's up to you. So this is your joint C, which is prismatic, and this is your joint D, this is revolute, and this is your prismatic joint. So this is also revolute. This is also revolute. So all pins you will consider revolute, all slide you will consider prismatic. Okay. So that's what I gave you here. Link 1 is fixed part, link 2 is handle, link 3 is cutting blade, link 4 is bar that connects this cutter and handle. Okay. So they have considered link 4 is that. And joint ABC is revolute joint. ABC is revolute, and D is your prismatic joint. Okay. So this all made your mechanisms complete, and this is how your mechanism is actually happening. Is it clear, Farah, or you still have any doubt?
It's clear for me, sir. Thank you.
Okay. Yeah. Anyone else? Okay, so I thanks all of you to attend this for attending this lecture, and I hope you learned something, and you will be able to complete your assignments. And by doing the assignments, because whatever we have covered here is only the base. When you will be doing the assignments, it will be like you will become more experts on doing these degree of freedom measurement. So that's all from my side, and I thanks Latifa for inviting me, and thanks all the students for attending it.
All right, thank you, Deep. So see you on a Thursday, and we'll have something to discuss just after this. So students, that's all for today, and thank you. See you on Thursday. You can leave the class now. Bye, everyone.
Thank
Bye.
you, ma'am.
Thank you.
Thank you, sir.
Thank you, ma'am. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, ma'am.
Thank you, ma'am. Thank
Thank
you,
you,
sir.
ma'am. Thank you, sir.